Joscha. He's going to give a talk about like the struggles of dealing with a large monorepo and hundreds of developers who all committing changes at the same time and causing the build to break. So, Joscha, come on in.
Thank you for having me. My name is Joscha. I'm an engineer at Canva, a design platform. And this is a very short and hopefully somewhat amusing story of how we introduced a bot named Larry Thomas. And for those of you who don't know, Larry Thomas is the name of the actor for an iconic character in the show Seinfeld. And yes, I was born in the 80s. So sometimes our build pipeline looks like this. And before you wonder, obviously that one green build is not a proper pass. It's a flaky false positive. And there are two main reasons why our build sometimes feels like this. There's one thing that we call a YOLO merge. It's meant for break glass scenarios, but it's a little bit overused. And the second one is cross effects. They're not necessarily conflicts between changes, but there's somebody making a change that affects future commits that are made. And a great example, and not very often example, but a great example is that somebody introduces a linting rule, for example, to prevent unused variables on a feature branch and then merges that to master. And now imagine 200 in-flight pull requests without that rule being merged to master, with 800 engineers approximately producing between 300 and 400 commits on master per day in our mono repository. That makes it a very, very easy way to break things that way. And the current chores to basically keep master unbroken, they're quite manual, or they were quite manual. And the first one is you have to babysit. Basically, you watch a few dozen pipelines for anomalies. And when there's a breakage, you investigate what's going on because you have to look into the build to find out, because there's so many different teams and so much different code that you first have to find out what's going on. And if you find out that it's a legit failure, you got to revert it, right? And then once you revert, there's obviously some communication problem because you got to let that poor engineer know that you just reverted 2 weeks of their work because of an unused variable somewhere in their code. And if they're lucky, it might even be their very first pull request after they joined. So doing this work feels a little bit like this. And thankfully, this chart is just a pre-made but very fitting chart from the presentation template that I used. But you get it. So this is not a real chart. But that's what it feels like. But in all seriousness, babysitting means that there's basically a private channel on Slack with literally every single failure across every single pipeline that we have, and you have to look at all of them. And the investigation takes a bit of time. It makes you switch context, and whilst you're investigating, usually somebody else is already messaging, so you don't really get any work done anymore. Not really meaningful work, at least. You might fix a few bugs or something. And with hundreds of engineers and thousands of builds per day, it's not pretty or fun. And we obviously all want to spend our time on things that are more meaningful than babysitting an automated system, right? Because that's what we have the automated system for. We basically want to get rid of this because it doesn't scale very well. And we're currently losing about 1 engineer a week on it. And that's likely to grow in the future if we keep on growing engineers and breaking things. And so, what is the infra engineer solution to work they don't really want to do it? They automate, right? And this was me, very enthusiastic, past me. And it should be easy, right? After all, it's just a revert. Like, we can do this. And obviously, everybody believed in this from the get-go. It was very, very simple. There was a lot of confidence, positive support for the project straight from the beginning. I was really hyped up. And when the first revert happened, people were actually surprised it worked. And I can understand, right? It's a very, very inexact science. And there were a few hurdles to jump over in the beginning that casted some doubts. There were some mistakes made as well, of course, as in any project. And some of the special challenges of this project were the ones that you can currently see on the screen. The paramount number one is that we really did not want any false positives. Like, especially we didn't want to automatically revert something that is completely fine. And you'd think that is easy, but there's obviously network, there's infrastructure failures, there's test flakiness that is variable based on what people commit and what they introduce, what tools they use. And we need to teach this to the robot, right? And robots, unfortunately, are not that great at pattern matching by default. Humans are, but we don't want to use humans. And we were also worried that a mindless robot would just revert the same commit back and forth when there's two unrelated failures that coincide, and we had like this flip-flop effect. And And so transparency was a special effort as well, because now there's no human anymore pinging people and supporting them through the troubleshooting process, etc. And the last one, and we only found that out after designing the system in theory, the revert is actually not always where the failure is. And that's a fun one, and I'll talk about this one in specific. So here you can see the process. And this is actually a code comment. I picked it out earlier. And this is a revised version of a prior, more complex but flawed logic. And there's basically two prerequisites. You can see them at the bottom. We assume that all failures are deterministic, and that there is a unique and stable key for distinguishing each step in the pipeline that we have. And if those are given, then one part of the logic, and that's actually number 2 in the slide, is the one that you all know. You have a pass in one build, and then a failure after. That's classic, right? Like a current failure just needs to revert itself. It's very straightforward. It passed before, failing now, revert it right here, and you're done. The other one, that's the more fun one, is actually that a current build pass reverts a future commit that's failing the build. And we only found this out after running the bot in dry run for a little while. Does anybody have an idea why a current pass might revert a future failure? You might have guessed it. Failures are faster because usually they are early exits. Think of a big build step that usually takes about 20 minutes in total. If it fails after 3 minutes in the build, then the build of the commit before is actually still running for potentially another 17 if the commits were close in time. And this time difference gets even bigger if you have build result caching. So the failure can't actually revert itself, as it doesn't know whether it was introduced in this commit or the one before, because that build is not done yet. So you can't decide there. So if you can't decide there, where do you decide? And the answer is obviously the build before that is still running. That is where you need to decide if the breakage was introduced in the future. And that's why the build of the current commit doesn't only look at its parent, but it also looks at its first child, and then reverts the child commit if the child build fails, but the current one passes. So each build needs to look at itself, the previous build, and the subsequent build, and where the revert happens is dependent on all of the states. Communicating this to the person whose pull request or commit was reverted is actually a little bit more tricky, because people don't expect a revert to happen when there's a green build, for example. And then the prerequisites that we made up, where I just said, oh yeah, this is a given. It reads very innocent, but we all know that this is actually a quite hard one. And I like this especially because most people that are outside of the build systems, they assume that the tests they write are 100% right, until they run at scale. And then even unit tests sometimes can become non-deterministic, and you can't rely on them anymore. And in order to solve that, we had to split commands, and we introduced a concept called marker files. And we upload these marker files as part of the build step. And then they are picked up by the build of the parent commit and the build of the child commit. We use BuildKite, and so these marker files are picked up by a post artifact hook in a BuildKite plugin that does the work. So they run independently whether the main part of the build failed or passed. So like even if the build step itself fails, that plugin hook is basically run, and we upload the file with the result. And splitting the commands into pieces was actually quite easy with Bazel. I'm only giving a Bazel example. We obviously have more than that, but it works quite beautifully. And it made our whole setup more resilient as a side effect as well. For when network operations, for example, we retry network operations multiple times, and we do not actually produce a signal file. So if they fail, we just silently ignore them for the case of automatic reverts, because you can't tell, right? It might be a wrong URL, or it might not be available right now. The builds themselves are then run without network access. So if the build fails, we can actually produce a marker file, as we know that it's a deterministic failure. And you can see from the code that we only produce a marker on a failure because a build pass often doesn't mean the whole step passed, as the build is often only producing artifacts to then be used in a higher order test, like an integration test or an end-to-end test, which the actual signal we want from the build step is. And running it looks a little bit like this. And this is actually an extract from an actual build. It happens in each guarded step. There's a failure, and then the step generates and uploads a marker file, pass, fail, deterministic or not. And this is simplified. There's a little bit more logic that looks at exit codes, handling seg faults, timeouts, aborts in different ways. And then the post artifact hook fetches that file if available, looks at it, and depending on the contents, at the marker file of the build from the parent commit or the child commit. It reverse matches the committer and the pull request, mentions the person that broke the build on Slack, opens the pull request with a revert, linking the original pull request, and mentions the committer and merges it. And that way, we've actually reverted almost 400 commits since October. I looked at the stats when I prepared this presentation, and we're only actually covering a subset of steps. And 2 reverts per day, it doesn't sound massive, but it is actually fairly substantial, as 2 red commits mean that master is red for quite a while, and people also branch off it, even though they shouldn't. And in average, it takes us about 10 minutes to find a broken commit, and that happens 24/7, no matter if anybody is on call or not. And that's especially great because we're now remote in multiple time zones, as most of you probably are since COVID. And we don't have to babysit as much. We still do, as not all steps are deterministic. And some network issues can't be fully mitigated until we have complete local caches. So sometimes when somebody introduces flakiness into a prior deterministic step, we do get false positive, which is really painful for everybody involved. And we're currently trialing a merge queue that should alleviate the majority of these breaks. However, as long as we allow break window scenarios in our mono repository, we actually do need such a bot. And just to close the loop, one of the people from the team that is on call told me that he didn't actually have to do a single manual revert in the previous week of on call. And my takeaway from that is that he's not actually faster than the automation anymore. So Larry Thomas is going to stay with us for a little bit longer. And I got the feedback that I select the most obscure names for my bots, and others seem to agree. I take it as a compliment for now, but potentially we might need to rename him. Well, that's me. Thank you very much, and have a great day.
So the first and foremost question I have, is Larry Thomas also for hire, available for hire?
He could be. It would be an open sourceable piece of code, I believe, because there's no core logic in it. There's one major problem with Larry Thomas. He was written as a prototype, and I wrote him in Bash, and it's not my proudest piece of software, and I think there would need to be some refactoring needed to make him for hire. But yeah, maybe.
Okay, it's pretty awesome. So let me take a look at the questions tab. Oh, and in the meantime, 3 questions have been posted. Let me take a look at the one with the most upvotes. Large commits that are reverted are quite painful. Are you also trying to encourage a culture of smaller commits?
Yeah, we do both. So we do encourage smaller commits because our review process actually favors smaller commits. So the smaller you commit, the faster your review is, which is kind of like a self-regulating system in order to get people to produce smaller commits. But having said that, I didn't talk about something that is actually important to the special. We only allow squash merges. And squash merges means that you actually only ever have a single commit that you can almost always revert. Because obviously when the build is run, usually the a commit changing something that makes it unrevertible is very rare. Like it can happen, but it's very rare. And squash commits don't need you don't need to make decisions like what parent you have to take and stuff like that. So yeah, we're cheating there a little bit, I suppose. It's a good question.
Okay, so there's one question that has like a crazy number of upvotes. So I'll ask that one. Have you looked at tools such as MargeBot and or Zool in order that also aim to achieve an always green master?
I have not. We looked at a bunch of merge queues. I'm not sure if MargeBot or the other named one are such tools. I'll look at them after. I might check the chat to get the spelling right and search for them. We looked at different merge queues. The problem with merge queues that are available out of the box is that they usually expect that you don't allow any direct commits to master. And we currently, unfortunately, do allow direct commits to master. I think at some point in time, we will need to revisit that in order to successfully get a merge queue deployed that actually functions the way you want it without side effects. But right now, the way we developed, it kind of requires being able to merge to master in some scenarios. Yeah.
Okay, thanks for answering that. So what I'm going to do is, there's still one small question. How do you avoid non-deterministic flaky tests landing onto the main branch?
Yeah.
Yeah.
Yeah. So we have a service that we use, an external service that is called Build Pulse, and it has an API, and we kind of track test flakiness. But it is not perfect because it uses the commit on or the builds on feature branches and on master to determine the flakiness. The only way to prevent that completely is to do something out of band, where before it merges to master, you run the test 200 times, and if there's one like flakiness, e.g., like it failed and then it passed or something, you just don't allow the person to merge it. And we don't currently do that yet. So there is some tests that inherently can be flaky, and I don't want to call out any tool names, but integration tests and end-to-end tests are much more likely to be flaky than, for example, unit tests. And so, for example, our integration tests, especially the one Selenium-based, they are actually not guarded by Larry Thomas right now. We just keep them for manual reverts. Yeah.
Okay. Well, thank you for giving your talk, and also thanks to the audience for asking all these good questions. Sure.
Yeah.
Well, take care, Joscha.